course, go ahead, and I'll post the slides too. I have
Thank you.
This is all everybody else's work, so I'd be happy to give you your work back. All right, so this is a figure that came. I think we all know this is a beautiful Obadiah figure, and so what I really like about it is it came out of our ACS Energy Letters perspective that we just submitted a couple weeks ago, and thinking about what really are the differences in organic polymeric semiconductors relative to inorganic materials. And so we can talk about this from a number of different length scales and a number of different behaviors and properties, right? So starting with something like a density of states, because we're a polymer, we have much more molecular-like behavior, and so we have a very different density of states, as well as, unlike inorganic semiconductors, which have a band structure, right? These density of states is highly localized effectively on individual chains or just a small interchain component, right? We have the soft material aspects that I've alluded to, of course, where we have interphases that they can swell and ions can intercalate, a solvent can come in, potentially redox molecules as well. So if we think about the hydrogen evolution, do we want our blended heterojunction to swell and do volumetric charge transfer, or do we want it to be all on a planar configuration, more analogous to the inorganic community? The other thing too that we've been talking about is this concept is, of course, band bending. When you take a conventional semiconductor and interface it with an electrolyte, there's a very discrete boundary, and then the energy levels will pin to the Fermi level of the redox molecule. But does that happen in organic systems, and can that happen if we have blends of donor and acceptor in order to dissociate the exciton? And what does that look like on an energy level scale? All right, and so within thrust 2, I think I'm gonna come back to this objective 2.1 because to me this really does sit more as a multi-thrust investigation. But if we've been really thinking about, we got started with these photoelectrochemical mechanisms and a prototype photocathode, and then we're gonna. My hope is that we're gonna come back more to this objective 2.2 as well as we start to get more into mechanisms. So this is Spencer's poster, and he will be presenting about the work on the center of the all polymer photocathodes for hydrogen. And so we have a couple of different pieces that are on here. So from NREL, we've seen some initial transient absorption measurements of the donor and the acceptor. This is a PCE10 donor polymer, and the acceptor here is N2200, and the change in those dynamics when they're blended together. I believe this is in a, it's been exposed to water, so it's not a perfectly dry, steady, a solid state film, but it's also not sitting in water, I believe. And I think Obadiah presented on this 2 weeks ago as well.
I think those figures, those TA figures are dry.
Those are dry. Okay, thank you. But there is differences when you do it in water or in dielectric.
Well, we got that we have that on the TRMC with the TA that hasn't been done yet.
Okay. And then I think Tim's group, so when I talked to Tim as well, they also have TA, so we should make sure that we connect with that. We've got some vibrational spectroscopy from Tim's group here. This is in operando electrochemistry, so under reduction conditions of the formation of the polaron on the NDI unit of N2200. The time resolved microwave conductivity measurements that Obadiah just alluded to in the low pH electrolyte system, as well as some initial demonstrations from the photocathode that we do in fact have the hydrogen evolution. So from the reports, if I can condense our quarterly reports down to one slide regarding thrust 2, what I took away is that we have the proof of concept again of the photocathode. Yihun has been looking at a bunch of different interfaces in terms of ITO versus FTO, trying to think about different types of whole transport layers, whether that's polymeric or a phosphonic acid or a particular oxide. One major thing that we've identified that if you look at these energy band diagrams here should come as no surprise in water splitting is that one of the competing mechanisms is always going to be oxygen reduction. And this is true regardless of what your material is. But in organics, we're of course probably going to be extra concerned about that because oxygen reduction in water results in hydrogen peroxide. And of course, hydrogen peroxide evolution is going to have some major consequences on the chemical stability of our films. And so conventionally, again, this is because oxygen always dissolves in water. This is a problem regardless of the material that you use for your photocathode. The mitigating it, reducing it, or changing, they're trying to deal with it, I guess is probably what I'm trying to say, is really, you want to try and introduce selectivity in your catalyst, right? So we've just been using platinum, so there really isn't much selectivity here. It's going to reduce oxygen and then it will reduce protons at different energy levels, but we could think about moving towards other types of catalysts where we would have a preference for protons. The other thing to it is as simple as just bubbling of nitrogen or argon in your electrolyte system and trying to reduce the amount of oxygen that's present, but you can see it. And it can be quite significant as well. One major hypothesis that we heard from Obadiah's talk a couple weeks ago is that there is this concept of the local dielectric is controlling charge transfer, which might also be a clever way to get around oxygen reduction here. And that we saw some changes in carrier lifetimes in terms of the ADA and the DAD molecular derivatives from Steve and Seth with the transient absorption and the time resolved microwave conductivity. All right, so where are we at? The ACS energy letters paper, I think that went in what, August 25th or something like that. We're starting to write some of the first heterojunction papers. I believe there's at least 2 papers on the molecular derivatives, maybe 3. And I know of at least 1 TRMC paper that is also in progress. All right, so where are we going? I think this needs to be a more integrated handoff with durability. So the focusing on the chemical reactions of including the oxygen evolution, as well as the oxygen reduction and the consequences of hydrogen peroxide formation. Another thing that has become very, very apparent to us is that N2200 is not going to be a long-term photocathode material. Just because of the electron affinity. It is too far from vacuum. So if you look at this little plot here, can you guys see my pointer?
Yep.
Yeah, okay, so if you look at this little plot, the electron affinity of N2200 lies right at about hydrogen evolution at low pH, at about 1. So if you increase the pH on this energy scale, right, water splitting then also goes up with increasing pH, the reduction potential. And so what that means is that any pH above 3, N2200 now has an energetic uphill to use electrons to reduce water for hydrogen evolution. And so this just is not going to work. And so we need to come up with additional polymers that have a weaker electron affinity or electron affinity closer to vacuum. So what the team has put together is we're starting to propose a larger material study. So if anyone is interested and wants to learn how to make photocathodes, this is pretty straightforward and would like to become involved. I think this is something that could be really, really fun thing to do as a multi-institution collaboration. Then I believe the plan is once we go through a bit larger materials study, what we would like to do is then come back with theory and more of the ultra fast spectroscopies characterization tools and ask the question of why are the best performing photocathodes performing so why are they better, like really. Other major needs is of course more whole transport layers. Again, thinking about going across the pHs, you want to think about the 2 pH extremes, either very high pH or very low pH. Very low pH has been very challenging to find something that is stable. And then again, pushing this thrust more towards that objective 2 is thinking about what are the mechanisms of charge transfer. And I don't have a figure there, but the way I'm thinking about it is if you want to drive a redox reaction to something, if you want to make hydrogen, right? You have this polaron. If we think about NDI, we have a polaron on the NDI unit, right? But how does that polaron change in order to drive that first proton and then the second proton in order to make hydrogen, right? What does that look like? All right. Coming back to that other piece as well, there's a subgroup that has started meeting. It's led by Mike Tony's group and has a couple of my group, NREL, etc. on it, and really trying to think about what this question of is, what is this equivalent of an electrical double layer in these pi conjugated polymer electrolyte interphases. And I think we've generally thrown away the idea of a double layer concept. And so trying to craft what that is and how we would characterize that. Right. And then thinking about too the connection to durability and how does swelling impact our charge transfer reactions as well. Okay, so with that, I wanted to take a pause again and just ask you, what of these projects would you like to engage with, just so that we can try and get an idea of where the distribution is across the center? Okay. All right, so where are we at? Let me pause again. Is there any questions, comments before I move on to the next thrust? Nope. Okay. All right, so thrust one, right, is really thinking about trying to characterize and define these polymer electrolyte interphases and understanding how these impact transports across multiple length scales and across time scales. Right, and so this has three objectives, although I do think that these seem a little bit more blurry to me on where objective one ends and objective two starts, etc. And how objective three, does that line back up in with the physical structure description, or is it part of a structure property relationship? Okay, so with this, I'm going to flip it now, and I'm going to ask you, which projects do you want to participate in first before I tell you where we're at? Okay, so it looks like the resounding question that everyone wants to, or not everyone, but the question that people are most interested in is how to counter ions impact polaron, possibly delocalization and transport. All right. And so we've got actually 3 posters that I would classify as being predominantly thrust 1. So this is Casey's poster, thinking about the different types of length scales of how we can characterize where ions are. And so on the left is a set of model systems of polyaniline, polypyrrole, and then the NDI, and a theory component from Joel and Megan and Chad's group, as well as some X-ray scattering data looking at as a function of doping, the changes in the structure, as well as on this other side here, we have a operando figure from Alberto's group of the cell that they have at SSRL, as well as some near ambient pressure XPS, including electrochemical XPS of Ian McCullough's glycolylated side chain component of N2200, right? As well as then again some photoconductivity. And so, the other piece that I want to really highlight that Casey did for her poster is this energy justice component. So she's been including that in each of her publications. So she was on the ECS energy letters piece. And this is something that I think we're going to do as well with the what's the equivalent of a double layer perspective. Right? So there's some nice, interesting technique development and thinking about changes in lamella structure as well as the side chain components. It's highlighted in Casey's poster. We have Henry's poster that is looking at the comparison between P3HT and PB-triple-T that has some theory contributions from Jean-Luc's group, I believe, some density of states estimations, and then some 2D spectroscopy thinking about static versus dynamic disorder, and the discussions about how these change as a function of the heterogeneity that we see in P3HT versus a very, very tight distribution in PB-triple-T. And then we also have Joel's poster that is predominantly looking back at N2200 and thinking about how these polarons are changing in terms of their optoelectronic properties as a function of oligomer size, and on the right as a function of the counter ion. And so one key result here from his calculations is that the polaron changes in extent of how it's extending across that NDI unit when there's the presence of a cation nearby, and then there's a comparison with the spectroelectrochemistry and I believe this is actually a pretty good agreement between the spectroelectrochemistry and the theory. All right, so summary of thrust 1, where are we at? We have some nice descriptions from theory. This is from Jean-Luc's group. It's been published in the Journal of Physical Chemistry letters of what does this polaron look like on an energy scale, a polaronic state. So if you haven't read this, I do want to call your attention to this paper. This is the appropriate way to be drawing these polaron energy states. And you'll notice that it does change. The energy levels do change when we form the polaron relative to the neutral, right? There's, again, the changes in these energetics, there's this oligomer length, the cation, as well as the crystallographic orientation. So there's 3 different crystallite features, edge on, face on, and standing up, that have been published for N2200. And so how does that impact transport? On the other side, on the p-dopable side, we have the thiophene-based systems. We have some work from Chad and Mike Toney, Chad Risco and Mike Toney's groups of looking at where the anions are. This was published in Chemistry of Materials, and this one is also a very interesting result in that the anion does not sit close to the conjugated backbone, but instead is farther up in the side chains, and is really not part of this coulombic interaction that's generally been hypothesized. We've got some active swelling of PRODOT systems from John Reynolds at Georgia Tech. That was also a submitted manuscript. We have the polymer. I'm sorry, Jinggao, I put it down here in P dopable. But we have the initial calculations on the polarons and bipolarons for the very, very large electron affinity PBDF polymer. And then we have the electronic disorder and dynamic correlations across the different thiophene systems. So Thrust 1 already has 4 published papers. If you haven't seen these, they're all on our specs website under publications. We have I'm aware of at least 1 more that's been submitted. I'm aware of 3 separate beam times that have been submitted by Mike Tony's group and Natalie Stingland's group, as well as from the reports, there's 3 or 4 more papers in progress as well. Right. The other thing too, yeah, please.
Erin, if I may just interject, I mean, one of the big things that has happened also is just the N2200 3 forms description, and that is taking quite a bit of time to fine-tune the crystalline structure, but I think it's an important step towards what will come afterwards in terms of the descriptions of the radical anions within both the crystalline phases and the amorphous phases. So this is something that we hope will get to a nice interaction with the Casey and the Tony group in terms of the characterization, as well as yours actually, in terms of characterization of these 3 forms.
Absolutely. Thank you. Yes, we had so just for everybody else, we had a University of Arizona meeting last week as well. And so thinking about exactly what Jean-Luc just alluded to. All right. I wanted to highlight this. This is a slide from Chimikara, but I think it's really important here and to touch on this, and as well as what Jean-Luc just said, is that we've got some major powerhouses in terms of theory support, but that on the experimental side, we really do need to be in contact and talking with them on a very regular basis about what our systems are, because the calculations do take a significant amount of time. Right? And so if I put this all back on everybody, right, and in my poll everywhere question, I asked you what you wanted to work on in Thrust 1, and the prominent answer was counter ion polaron interactions. Right, so think about what you've been working on. What's your electrolyte? Who else in the center is working on that exact same electrolyte? Do we know? Because that was, while it seems like it's kind of obvious, it's not. And I think too, I've been asked this multiple times from both Jean-Luc's group and Chad's group, is what ions are you guys thinking about? What solvents are you working in? Right. And so we really need to be conveying that so that their calculations can provide us with the information that we want. And my understanding is too, this is really coming along in terms of the molecular dynamics and the DFT back and forth feedback, and trying to, exactly as Jean-Luc said, get ideas about crystallites as well as amorphous for these polymeric systems. Right. The other thing that is very, very obvious is that we've got a wide variety of characterization capabilities, but they seem to be operating a little bit by themselves, if that makes sense, in that, you know, we see in the project descriptions, there's reference to GWAX, but there isn't how is the GWAX going to be used, or we see FTIR, but it isn't, this is what I'm looking for chemically, or the Raman, etc. I'm not picking on anybody. I just want to, as we think about evolving our subgroups, we have to really start thinking about how we can ask big level questions and then try and do some of these handoffs between the characterization and the theory. Right, so what I saw as future directions and team needs for the charge transport is, again, focusing towards the crystal structures and orientation dependent transports. A big one that I think I'm sorry, I failed to leave on here is also a lot of technique development, which is really cool, is pushing things more and more towards operando. All right, we've got a lot of ion polaron interactions, and so thinking about our electrolyte a little bit more detailed, what solvents do we want to use? Do we want to promote swelling? What if we use a solvent that does not promote swelling? How does that change the transport? What about the anions and the cations? Which ones and why are we using them? As well as if we connect to the transfer thrust, is thinking now about new materials. Should we be establishing structure property relationships and now moving past N2200 and PV in the next few months? And where are we going to go?
Erin,
Yeah.
I have a kinetic question regarding that particular point.
Okay.
There's a lot of investment right now in N2200. And the question that I'm trying to get some guidance from you is, we could go on for 3 years characterizing crystallinity, ion interactions with that. And in your mind, how quickly do you think we should be really thinking about pivoting from that to a polymer that, or polymers that are more energetically aligned with some of the needs that we need, versus keep plowing and expending resources on that when it may end up being not that relevant in the final analysis? Do you have any thoughts on that?
Yeah, thank you for asking that. So I'm gonna answer this a couple of ways. I think the first thing that I'm gonna say is N2200 was the model system that we picked to get started because it was commercially available. From a transport perspective, N2200 is not good. It's slow, right? It's not a high mobility N-type polymer. Because the polaron is so delocalized, or not delocalized, excuse me, because the polaron is so localized on that NDI unit. The second thing is that in organic electronics, in my perspective, you can do some very, very nice technique development with well-established polymers, but it's harder and harder to do very high impact on systems that have been around for 15 plus years. And N2200 is one of those. And so to me, I think what we should do in the next few months is really take what we can from N2200. What have we learned? It's allowed us to do some technique development. All right. It'll allow us to do some questions about polaron cation interactions. But then I do really think that by January, we should, especially in the transport thrust, I think we should be starting new areas and new projects and thinking about different types of polymers, maybe sidechain free polymers, for example.
So just not to get you too far off track, at some level, historically, I feel like we kind of chose these polymers because of things that we knew about them and their availability. And I think that's something even between now and January that could be worth spending time on, is a complete retro analysis. And that is, what do we want to do? What are the attributes of a material that would do what we want to do? And how do we map that back onto chemical structure and polymeric structure to begin to ask, A, either how do we make the polymer that we want? B, how do we identify a polymer that already exists that may come close to meeting these criteria? Or C, how do we take a polymer that may already exist that doesn't meet these criteria but comes close and modify that? So it's not basically saying, okay, let's drop what we're doing, but begin to get people into the mindset of thinking about what is it we're really looking for in our material.
Yeah, thank you. Yes, I think that's that. Mike, can you please make a note? I think that should be absolutely one of the things that we discuss in that October 2nd meeting when we have all of the PIs together.
One of the things that's interesting with the three forms, with respect to what you said, Erin, in terms of the localization of the on the NDI, is the fact that there are forms indeed that form one that provides for NDI, NDI pi stacking interactions. And so seeing how the interchain interactions evolve as a function of the structure can be, I mean, will be an interesting thing as we complete the work on N2200 and can inform indeed what can come afterwards.
Okay. Shingao, did you have something to add too? So you turn your camera on. Nope. Okay. All right. So let's start with this and let's just do a visual representation. Which solvent, anion, and cation system are you working on with N2200? Because I could be also completely wrong and everybody's doing a cohesive component. I'm seeing a lot of potassium, water, acetonitrile, variety of different anions. Looks like we got some tetrabutyl ammonium. Then I see a couple of hard anions in there, some zinc, some cesium, sodium. All right, so if we're going to try and answer the question as a center, how are we going to characterize polaron-ion interactions? Looks like we've got a couple of different kind of bins that we could start to put this into as a team. And so again, I really want to encourage everybody to just engage with some subgroup meetings and let's try and get some of this stuff fleshed out a little bit better about what is it we're really trying to learn from our changes in the electrolyte composition. All right, so with that, I'm going to unfortunately go through a little bit faster on the durability thrust, just so that I keep on time here. And so again, the durability is really focused on the mechanisms and degradation pathways, which can include chemical and mechanical. And the three different objectives are focused on the molecular and structural features, the relationship between the features that we want and the polaron delocalization extents, and the reactions that we're trying to drive, as well as the functionality and stability with repeated cycling. All right, so this is Joe's poster that just pulled together a variety of different kind of scientific questions about the different polymers that the center is working on. So on the left side is some FTIR, it's ex situ, as a function of with and without TFA, an organic acid as a possible proton source. And then on the bottom, we've got changes in the peak currents of the N2200 as a function of pH and oxide support, which motivated on the far right side over here the phosphonic acid cross-linking approach from the Marder-Barlow groups and the controls associated with that. And then in the middle here from Zhengao's group, we have some a model approach to degradation, which is usually using the UV component of environmental chamber, looking at first just changes in absorbance, and then I'm assuming moving towards inclusion of this in electrolyte and how does that change the chemistry component, and then as well again this BBDF highly conductive N-type polymer that has some very interesting components in terms of the polaron and bipolaron in the presence of protons. All right, so this one was a bit harder to pull together, but the accomplishments that I was able to pull from the reports is there was the large pH study, round robin, that we used to get kicked off back in January, and the approaches to increase the adhesion do seem to be working in terms of the cross-linked, and I think there's some new questions that are starting to come out of this project. So I know that there's of at least 2 papers in progress, and that what we've identified from the reports for team needs and future directions is, again, thinking more about the chemistry changes of these systems as a function of carrier density, probably microstructure, solvents. I could also see, excuse me, sorry about that, in terms of the strength of some of those ion polaron interactions that are coming out of thrust 1. And then again, the reactions with protons and even possibly hydroxides or hydrogen peroxide as well. One thing that I saw as a need is that we talk about durability, and there's a lot of, there was alluding to cycling, but I don't know who is doing the cycling. So we need somebody to take the ownership of that. And I think one thing that we'd had, but just hasn't come forward yet, is a battery or a capacitor-like device to use as an application, so that we can think about how to connect our mechanical and chemical durability and transport concepts to something to show that it impacts performance. All right, so this is my very last slide. What have I missed? When to meet as subgroups and how to get those going. I don't think it would be good for me to tell you when to meet as subgroups. So what I've seen with the subgroups, I'm going to start just answering these, and then again, this will all get captured. I would suggest that subgroups should probably be meeting about at least once a month. So depending on where you're at with the projects, I know the CU NREL team meets, is it monthly? The U of A teams have just started meeting monthly. I know the theory group meets, I think, bi-weekly. So we have, what my hope is with the subgroups too, maybe this will be a little bit of a motivation, is we'd like you all to get on the calendar to do this 1 hour, tell the center what you guys have been working on and what your group is where you're going. So maybe what we need to do is, once the subgroups are organized, and this is again through the thrust leads, so Seth and Jingao and Chad and Tim, then what we'd like to do is get you guys on the calendar so that you can plan your presentations, and emphasis on the students and the postdocs will be doing the presentations. And the hope is really that it will be tag team, you know, between institutions. So you're going to see one from Spencer and Henry in 2 weeks. All right, so I think that goes to a fixed schedule for presenting the large meetings, so we aren't constantly searching for folks to present. That's our hope, is that we're going to get these 6 to 9-ish subgroups set up, and you all be on the calendar, and we'll just rotate through those. Are hydrogen generation and batteries in the main application driver? And if so, are the polymers we're discussing, are they appropriate models? Yes, I think that was the general idea, was that hydrogen generation or photocathodes and batteries or some sort of energy storage type of application. And what I tried to convey is that probably M2200 is not great for hydrogen, and probably is not going to be great for a battery type of application. Let's see, what else have I missed? This went fast on me. Calendar of subgroup meetings and who leads, we can do that. Are there subgroup leaders? Oops, I'm sorry. Shoot. I lost them all. Anybody else want, is there anything, maybe you can just do this without technology. Is there anything else that you want me to mention in the last minute or two? I realize 2 people have to go.
Well, they're regarding the subgroup leads, at this point, they have not been assigned or determined.
Do we have a list of the subgroups, or at least a start at who's participating in each? Maybe some sort of spreadsheet so people can kind of see how those are forming, where they can plug in and add themselves to a subgroup, or say, hey, I shouldn't have been on this, remove themselves from a subgroup. I think we might need to see those top 10-ish projects and who's in each one. I think that'd be very helpful that everyone has access to that.
I think the thing that we can do, maybe to start this, is I know there's teams that are happening. So for example, there was a previous call with the cross-linking stuff that I was on the hour before. So I would consider that one subgroup, right? So we can self-identify that that's being led through Seth's team. I think there's certainly the other example I can think of is just in the meeting that I've had is the one that Jonathan is leading on what's the equivalent of the double layer perspective. So we can self-identify that as well. So if people could just, whoever is leading that particular team, if you could just ping Mike and Jen and tell them who's in your subgroup and what you're working on, that would probably be the easiest to get started. And then I agree with you, Alyssa. I think we can share that with everybody else so that people who want to be involved in those projects can get involved.
Well, another thing that can happen is I will, once we get all the subgroups and, a smaller list of project names, that can all go into Basecamp and hopefully be a little less confusing, and just a little more, just less confusing.
I mean, you do have that list of projects that Erin showed earlier, right? So it would be great, Erin or somebody else, go through that list and really simplify and
Well,
put that in.
That's my problem, Tim, is I need your help. I need your help to go through those. Erin has, limited, her time is limited. I am not a subject matter expert. Can I schedule time with you and I'm happy to do this with you, and I'm happy to do it with all the thrust leads, but I think that's where it should come from.
That could work too, yeah.
I propose we do this in the next management meeting, actually, is get this down to our top 9, 10 projects and decide as a group what those are called. And then people, we can kind of tentatively put people where we think they go, and let then the group decide individually, like, yes, I should be there. No, I shouldn't be there. And really let's hammer those out. I think that'd be a good management team exercise to do together.
Yeah, I support that.
Okay.
Very good idea. Are the thrust leaders invited to the management meeting? If they're not, they should probably be there.
Yes, they are.
Okay.
That's our Monday other meeting, Tim, that you go to, remember?
Okay. I thought it was just going to be a fixed shot in the center. I'm sorry.
Okay. Anything else? Was this helpful? I hope this was helpful. It was helpful for me, at least, to kind of pull it all together is what I saw.
I thought it was very helpful.
Yes.
Okay. Okay. All right. Thank you, everybody. I appreciate your time. If there's something that you thought should be on the slides and it wasn't, it's because I don't know about it. So please shoot me an email. And I look forward to seeing what's going on.
Bye, Erin. Thank you.
Bye.
Thanks, everyone.
Sorry, I'm just reading the chat. I didn't get to read the chat while I was talking. Okay. All right. Thank you, guys.
Thank you. Do you need anything right now, today, later?
Nope, I'm good. I'm at home. Jen, the meeting with the undergrads this afternoon, do you remember what that's about? I don't remember anymore what the point is.
I think that was just kind of like our general, get together meeting, see how everybody's doing.
Okay. Can we add a virtual component for that so I don't have to come in just for a
Absolutely. Yeah, I'll go ahead and create a Zoom link and send it out.
okay. Okay,
Yeah.
cool. All right, thank you.
Hey,
You're
I'm
welcome.
on campus right now. Is there anything you need while I'm here?